Dilek so kindly mentioned, I'm an engineer at the New York Times. Most of my work is specifically around Android development and whatnot, but I have a background in machine learning and AI, and I spend a lot of time, including my side time, on machine learning and AI projects. So specifically, and especially this year and the last, I guess, several months and before that, I've been deep diving into computer vision work, a little bit more background, a lot of work that I've done in the past years and years ago, and especially for like my educational work, academic work in my master's program and whatnot, involved a lot of computer vision stuff. And since then, it's evolved quite significantly, the discipline, like incredibly fast. So I'll just go into the actual topic. We're going to be talking about generative adversarial networks. And if you've been paying attention to the AI news, and especially the last few years, even past this last year, which was massive for AI, you would have come across this term, and I will go more into it. But yeah, it's just a massive field, and it's getting more and more relevant, and especially this year, topics in this particular category of AI generation, image generation, and AI synthesis of different sounds and other things that generative adversarial networks tackle are involved in is exploding. So it's good to know about this stuff, and it's good to be aware of the different implications of this technology. So the structure of this talk, I'm going to go over this a little bit. So the initial part is just going to be an introduction to the background of where this is all coming from, and just a few precursor things. I'll be going next into the basic theory of generative adversarial networks and touching a little bit on the pieces that put that together in terms of the AI stuff. I'm not going to go super deep into like AI and whatnot in general at the like mathematical level or anything, because I kind of want to present this as like a holistic, like larger scale overview of this entire body. But in a future talk, we can go deeper into that or something. The advancements in generative adversarial networks, and they have been, again, at a rapid pace. AI imagery and GANs have been evolving at a massive clip. So we're going to go over some of that. The basic operations, so kind of how these work under the hood to do what they do. Some of it's a mystery to people, and into many ways, AI in general, the way it works is mysterious. Yeah, we'll try to demystify some of that. And professional tools for this. So yeah, at this point in time, there are several tools that people use to build and work with AI imagery. And you've seen DALL-E, you've seen other tools that are out there. I'm going to try to talk about some tools that are not necessarily as familiar to many people in this world. And so that's probably, if you do work with this technology, you're probably familiar with it, but I think the vast majority of people are not, and some of it might be enlightening to the kind of current state of things in terms of what's being output. And then we're going to talk about like the crux of the talk, synthetic media and deepfakes. So there is a lot of material here. This might go a little past the intended boundary of time, but I'm going to try to like be thorough in each piece enough so that you get everything. And a lot of code went into putting in the demos into this. I did a lot of code work. There was a lot of tooling, but I'm not going to go too much into the nitty gritty like details on the Python level here, because that will take away, I think, from the flow of this and the understanding. But if you're interested, that's something that, again, we can talk about at another time, or there's tons of resources out there if you can collate together, and we'll try to put a resource slide together to start gathering some of that if you're interested after this talk. Okay, so again, GAN stands for Generative Adversarial Network. And I will go into all the details into what these pieces mean for those who are not familiar, but generative refers to generative AI, and what that is. We'll go into that a bit. Adversarial, that's the key component of this. And at this level, for those who are not familiar, adversarial means, combative. And there is something about this that's just combative in general, but that's a core component of how the system works. And networks, it's referring to the neural network, which is the core AI component that powers all of this stuff. So I will start with a New York Times article that came out in 2020 by Kashmir Hill and Jeremy White. The title of the article was "Designed to Deceive You. Do These People Look Real to You?" So I'll start the video so you can see kind of the scroll through of this article. And it's a fascinating article because a lot of work went into it. But as you can see that there's this person that is transforming into all these other people. And the key thing about all these people is that none of them are real. Like all are AI imagined. Okay. So this tool, this technology is based on a underlying core piece called StyleGAN, which was created by NVIDIA. And the New York Times worked with you worked with that team to make this article, and you can go to this article and play around with it. It's actually quite fascinating. The point of the article, besides showing you kind of the capabilities of StyleGAN, was to introduce everything from everything related to generative AI at that point in 2020/2021, that year that was coming up after, which included the dangers of fake faces, including false profiles, being able to unlock smartphones with Face ID, things like that. And the great thing about the article was that it gave an overview of ways to detect fake people in images, like looking at things such as strange artifacts, malformed appendages. And if you look in the news, you probably are familiar. If you see a lot of AI generated people, you'll see things that like they have extra fingers, or they have weird teeth, or they have like, strange people that are like weird blobs behind them in an image, or like distorted backgrounds. These are kind of giveaways. And so this article attempted to go into that a bit. Next, now we're going to just talk about GANs. That was just kind of a soft introduction into the capabilities at a high level. So this person on the right, a lot of people may not know who he is. Some of you might. This is Ian Goodfellow. He is also affectionately known as the GAN father, because he created the Generative Adversarial Network. So just quickly, he works for Google DeepMind, and he presented his work on the Generative Adversarial Network at a really popular conference called NeurIPS, NIPS, which is famous for machine learning. And like the top machine learning people submit articles every year to this conference. And it's really, if you're into machine learning, I would suggest trying to submit to this conference, because your work would become possibly world famous. But they do have a bar of submission. So anyway, he presented this paper in 2014. So GANs are about 10 years old at this point. There's actually if you watch Lex Friedman, he did an interview from 4 years ago with Ian Goodfellow, where he's talking about how he came up with this idea. And apparently he was at a bar drinking with friends, and he just came up with this idea. And he said if it wasn't for drinking or being intoxicated, he would have completely dismissed the idea. But apparently that opened up some innovative new things in his mind. But he also said that you shouldn't drink to spur new ideas in your mind. So anyway, so why GANs were revolutionary? Because they did something called learn the underlying distribution of the data, rather than rely on humans to supervise. So just a quick precursor, GANs are not the first generative AI technology that's been out. Generative AI has been out for a long time. It's just nothing that has been in people's eyes until recently, until the social and technological implications have been really present to people. So older versions of generative AI were things like, you might not have heard of them, but you can look up the terms, something called like restricted Boltzmann machine, autoencoder. There's a lot of different older Gen AI technologies which did generation of things, but they were pretty hard to control in terms of what came out. So they were essentially useless until the GAN was invented. So when the GAN came out, like, it was, again, revolutionary, but the initial generative adversarial network had issues with it. Like one of the most well-known issues of the time was something called mode collapse. And what that meant is that it could generate like realistic replicas of things, like with variations in it. That's what the whole generative part was. But if you didn't train it right, it could generate the same thing over and over again, despite you asking for something else. So if I asked for a chair, if the GAN mode collapsed, it would keep generating maybe like a table or something over and over again, regardless of whether you asked for it. So what happened was there were improvements to GANs over the years, which led to the improved capabilities to generate things that you want to see, up till the present day, where now you go online, like to DALL-E, 10 years later, you can, or any of these image generators, you can generate like whatever you want pretty much, like fake imagery, real imagery, you just ask it, and a lot of the times it comes out. But there were several progressive steps in doing that. And so the first two major evolutions of the GAN was the DC GAN and the W GAN, which I'm going to go into a little bit. And yeah, if you want to, there's some very interesting information out there. You can find it all if you look them up. So compared to other generative models, so 2022 to 23 was like huge for generative models in general. Besides generative adversarial networks, which were kind of the precursor to the more powerful generative models that are now popularized out there, you have what's known as the diffusion model. And the diffusion model operates similar to the GAN. I'm not going to go into that in this talk, because the diffusion model has a lot of its own different ways of replicating and generating new imagery, and it has its own technology behind it. It's worth its own massive discussion also. The transformers, which everyone knows about, ChatGPT, things like that, those are models that work with text and generating new text and sentences and paragraphs and et cetera. And if you're into AI at all, these are familiar to you. You probably use ChatGPT on a regular. So that's based on the transformer architecture. And then the variational autoencoder is essentially, at one point, was a kind of a competitor to the GAN model. It's not exact. We're not going to go at all into the VAE, but you'll often see them described in literature along with GANs as well. And again, some of the players I listed here: OpenAI, obviously everybody knows them; Stable Diffusion, the most popular, probably the most popular open source generation tool. Google, of course, with Google AI, and Midjourney, which is probably the most popular tool to generate realistic imagery. So those are just some major players in this. So I'm going to start with some basic theory, but then I'll progressively build upwards, because, like, again, I want to present everything here from like kind of a way that you can kind of build to like a story of like where things make sense at a high level. So we'll start with the basic artificial neural network, the ANN, as people call them. So neural networks, one of the most successful ML architectures out there. They're a computational model inspired by the neuron-based structure of the brain. So they're inspired, that's the key word here. They're not exactly similar, but they have some similarities. So basically what the neural network looks like is that this picture on the right is a picture of like a neural network operating to classify something, input into it which is a dog or a cat. Like, let's say it gets an image and it's like, okay, what is this? It determines that it's a dog. What is this? Another image could be a cat. And again, the neural network consists of these nodes here are what make the determination on whether it's a dog or a cat. So the section in the middle is called a hidden layer. Each of these groups of circles or neurons, as they call it, digital neurons, is a layer. So you have the input layer, the hidden layer, and the output layer. And you can have many hidden layers in here. The more hidden layers you have, in some cases, the more powerful the neural network can become. So each neuron processes information and passes it through weighted connections, allowing the network to make predictions or classifications. I teach a data science class where I go into this a bit, and there's tons of literature on exactly how this works. For now, all you need to know is these lines that connect the neurons together have different weights. And these weights are how this is essentially called the latent space of this network. And that means where the actual learning is. That's where the intelligence is. It's in the weights of these connections. And so that's how predictions are made. Once you train this network, it can then, it has learned, so now it can work and differentiate between the cat or the dog. The neural networks use algorithms to adjust weights over time, and they minimize their error prediction. So at first, what's going to happen is the neural network is untrained. So it's going to try to classify between a dog or a cat when you're training it, and it's going to do it pretty badly, likely. And over time, this system learns. The learning part minimizes the error between detecting whether it's a dog or a cat. And there's two things you'll hear about often if you're studying neural network architectures and machine learning in general, called gradient descent and back propagation. I'm not going to go too deep into this at all because this is where the mathematics comes into play. But essentially, these two techniques are how the neural network constantly, it makes a prediction, it checks whether it's good or bad, it goes back, and then it keeps checking over and over again until it refines its prediction. And you can kind of think this is how a person learns over time. After a lot of practice, it will eventually get good at doing something. So that's essentially how this thing is designed. So the next thing. Okay, cool. So there's classes of neural networks things. So things that neural networks do. So if you've done any kind of data analysis, you'll know about regression. And regression is basically a technique where if you have a bunch of data, you fit a line to this data, and you can make a line or a curve or something like that. You fit some kind of spline to the data, and you can make a prediction on that data. So like if you can predict like 5 months into the future or something based on where the previous data told you the curve should look like, how it should bend. Then you also have classification. So that's where this example I showed you with the dog and the cat, it's telling the difference between two things, like whether it's a dog or a cat, and it does so through things like creating decision boundaries, or like a boundary in the space of different possibilities. So X is one side, red, these circles are another side. It's not this simple, by the way, but I will say that this is at the high level enough to, I hope, convey what it's doing. And then there's the task of generation. So it's kind of interesting, right? It goes from this simple line to this simple line to then this crazy thing. And so this is what neural networks can do, actually. It's kind of fascinating. They can generate new instances of output. But it's, again, not that simple, but I just wanted to give you overview. So the basic neural network evolves into something called the convolutional neural network. And the convolutional neural network is a more advanced kind of neural network that has additional pieces to it. And it's specifically designed to classify imagery. So what it does, and this is kind of the magic of how everything works these days. This convolutional neural network, which again, I won't go too deep into, it automatically learns what is important in an image. And the very interesting and amazing thing is you don't have to differentiate it too much. You don't have to play around with it too much. It just somehow has the ability, and somehow is in the math, but it has the ability to learn things that will tell you whether something is a truck or a car or a bicycle or a bird or a plane or a person. This is I consider this one of the closest things to magic in neural network architecture, but it is at the foundation of all other things. And this is an example on the right of it classifying people and moving, creating boxes around these people to move, to see where they're moving. I spent a lot of time with this particular technology when I was being educated in my learning years ago. And so this is, again, the foundation of everything, but we'll leave it at that. So one other detour before I go into the core piece. We'll talk about game theory a little bit. So if you've ever played chess or any game, or most games, there's an optimal strategy in how to play the game, and there are many strategies on how to play the game as well. So the theory of the game theory, it decides, or it's kind of like the framework of how people decide how to play the game, a particular game. So and people can play in many different ways, but there's an optimal play strategy in many games or most games called the Nash equilibrium. And we're going to keep it at this because game theory is a fascinating discipline. But all I want to convey to you is that there's a best way to play most games. Okay, and that means if the players are playing to win, every player in the game will be playing according to their Nash equilibrium. That's the high level way of saying this. So any competitive system can use game theory. Most competitive systems, let's say that. Economics, politics, traffic predictions, predator-prey systems where you have wolves and rabbits and things, they can play in a survival situation that can be framed as a game, even though it's not a game for them. I mean, it still can be framed as a game mathematically. And so this idea of game theory can be extended to machine learning, so that if you have the game being played by the neural networks themselves, which are, kind of like a proxy for people in a way, then you can have them competing to do something very specific, which is called adversarial. It's called adversarial learning, adversarial training. It's the adversarial dynamic in the generative adversarial network. So essentially, you set these two networks up to play a game. And this image on the right, I'm not going to go too deep into it, but it's the canonical example of game theory, which is called prisoner's dilemma, which is if two prisoners get incarcerated, one prisoner has to rat on the other prisoner, or they both rat on each other, or neither of them rat on each other, then they do different amounts of time. So there's an optimal way for each of them both to play this game of not ratting or ratting that they do the least amount of time. It's kind of fascinating and opens up the entire theory of game theory. So if you get a chance, I'd say look at that. But let's continue with the main topic. So adversarial models, neural networks plus game theory. And again, this is fascinating because Ian Goodfellow and a few other people that came up with this, like, it's hard to understand how this works, honestly. Like, even if you're a trained machine learning person, it's like, why does this work? It's many questions in AR are like, why does it work? And there's many mysteries that people don't know the answer to as to why things work. Okay, that's the best answer I can give you right now in this short period of time, because it's quite a deep discipline. But basically, the GAN, generative adversarial network, consists of two convolutional or convolutional-like neural networks. That's why I mentioned those before. The generator and the discriminator. Okay, and depending on what type of network GAN architecture you use, these are called different things. For example, in some GANs, you have the generator, but you also have, instead of the discriminator, you have the critic. The naming is kind of important as to what the adversarial network architecture does. But for now, just know that here's one neural network A and here's neural network B. And these two neural networks are essentially designed to compete against each other. So what game are they playing? That's the question. So the first network is set up to create a bunch of fake images. And it starts with random noise. A lot of machine learning models and algorithms, they start with what's called they start with random initialization data, because that's the best they can do. That's a huge theory on its own, but for this, just know that for this setup, they start off with like a random, like noisy white noise data set. And the discriminator network, what it does, it says, oh, okay, is this something that I know of? So I trained this discriminator based on real images, like faces or chairs or birds or something. And it looks at what the generator says to it, and it's like, okay, generator, did you give me a bird, or did you give me a person, or something like that? And in the beginning, the discriminator is going to be like, no, that's not, what you gave me is garbage. Okay, so it's going to say that you're wrong, it's nothing. And so it's going to go back to the discriminator, the generator, and the generator is going to try again. And the generator is going to keep trying and trying and trying and trying until it actually improves, until the point it can fool the discriminator into thinking that the thing that it output is a real face, or is a real bird, or is a real chair. This is kind of, again, this is the game that's being played. The generator tries to fool the discriminator. And you would think, like, being into algorithms and coding, like, what is going on here? I mean, but fascinatingly enough, according to the mathematics and according to the output that you've seen with your very eyes in generative imagery, this works. Okay, this somehow works. So eventually the generator gets good at fooling the discriminator. The discriminator keeps having to outplay the generator. The discriminator has to keep getting better at trying to be like, oh no, you're giving me garbage. And both of them improve each other's gameplay mechanic until they reach their Nash equilibrium, which I talked about in the previous slide. And at that point, they're playing at their optimal play state, where the generator is consistently producing new and better images, and the discriminator is getting better at discriminating between fake and real images. But the generator is typically winning out. And so again, that's what I mentioned, the Nash equilibrium. So again, that's a lot to absorb probably, but this is essentially the core mechanic of how this works. So this is more of the facial example here. You can train this network, dual network architecture on anything. I can pass in a bunch of faces, right? This is the sampling data to the discriminator. So the discriminator is trained in this kind of supervised training mechanic on a bunch of facial data. The generator, now again, it starts with random noise because, you know, in most cases, that's the best you can do. You don't know anything, so you start shooting in the dark. Generator eventually generates something that looks like garbage until, again, as we talked about, it eventually gets to generating like a real better output. So let me just, give me 1 second. So one thing I mentioned here at the bottom is that mathematically speaking, because some might be wondering why this works, what it does is that there's a metric called the Jensen-Shannon divergence. I'm not going to go too deep into that, but there's something that has to convey the knowledge that the generator is getting closer to the discriminator and to creating real things that can fool the discriminator. So this number, just think of it as a number, is called the JSD, and it's a metric that is basically talking about how close you are, right? So if you're familiar with neural network architectures and you know about the loss functions, right, you'll understand that this is essentially what's trying to be minimized. That's the error metric that you're trying to minimize between the two things. Okay, so now we talked about the basic theory. Now we're going to talk about the advancements in generative adversarial networks. So the evolution of this. Now on the left, right, you see how things started, right? This is like, these are clearly not, these are faces, they're something, and you would have probably been impressed in 2014. Today, you'd be not impressed at all. This is where we've evolved to by 2021. Now it's 2024. Oops, I clicked the chat by accident. So in 2021, this is where we got to. And how did we get here? And by the way, we started off with DC GAN. We started with the regular GAN and then DC GAN. And then by 2021, we got the style GAN. And this is trained on the celebrity data set. So these images are actually supposed to look like celebrities. I mean, they don't look like any particular celebrity, but they're trained on the features of celebrities. So they may resemble a famous celebrity. So the first improvement that allowed to get to this was the development what's known as the Wasserstein GAN. Okay, the Wasserstein GAN changed the metric that was used. So as I mentioned in the previous slide, the metric was called the JSD, that number. That number turned out not to have been the best number to calculate more realistic faces. Again, this is the closest I'm going to get to math in this presentation because I don't want to overwhelm people. But what I will say is that once this metric was replaced and a number of other advancements in the Wasserstein GAN, realistic faces was a reality by 2017. And that's when, around the time the deepfakes started becoming a problem. We'll go into that later, but the Wasserstein distance, or Earth mover distance, EMD, measures the cost of transforming one distribution to another. So one is the distribution of real data, the other is the distribution of fake data. And so there's some transformation that occurs that essentially tells the networks that this is, I just need to move this much here to let you know that this is real. These are real faces. I need to move my fake data set this much to let you know that this is a real face data. I'm not, again, the reason why is that there's this idea of gradients. I mentioned gradient descent before. There's this idea of like the direction of reducing error, and that's what gradient descent is. So the EMD, the Earth mover distance, like allows you to create a meaningful gradient. And that just means that like it doesn't get lost. The older metrics, like the network can go do crazy things and it'll get lost. This double Wasserstein metric, or EMD, allows the network to not get lost, and you can generate consistently good, realistic looking faces. So the GANs trained with the EMD distance tend to be more resistant to mode collapse. That means, again, I mentioned one of the problems with the original GAN architecture is that it kept generating the same face over and over again for different output requirements. And so that is called mode collapse because the same face is the same mode of the data. So this metric avoids this, and other things help about the Wasserstein GAN avoid mode collapse. So next, I'll start to go into the how the visualization, because that'll be more interesting to more people than that. But that's just a little background. If you want to read the paper is super interesting. It's very deep, lots of math in it, but I think if you're really interested in the subject, it's worth the read. The Wasserstein GAN was introduced in 2017 by researchers Martin Arjavsky, Sumit Chintal, and Leon Botu. I hope I'm pronouncing those right. And after the introduction of the Wasserstein GAN, like there was an immense boom in interest in generative imagery and deepfakes. Like that's again because now you could generate realistic faces, and I'm going to go into that in the next slides on the realistic faces. But the important thing that Wasserstein GANs in practice allowed you to do was parametrically control outputs. That means I can smoothly like transition. If you remember the beginning of this presentation, you saw the smooth transition between different people. That started with this Wasserstein GAN. And so here's a like interesting demo that I put together, and you can actually code this up in Python if you want to like really understand how the Wasserstein GAN works under the hood. You can build this. There's this anime face data set online. If you're into anime faces, it's trained on a bunch of different anime faces from different anime. And I'll just play the visualization. And I added some interesting music here just because, I don't know, there's some kind of like ethereal element to this. So what this is doing is that this is training the generative adversarial network is training right now against different face structures, different anime face structures. And it's essentially transforming from one to the other, right? So these are different outputs that it's learning to produce over time. And again, it looks weird, right? But that's what it's looking at, different facial features and reconstructing new things out of those features parametrically, like it's smoothly transitioning. You couldn't really do that effectively with the older GANs. And this by itself was a powerful mechanic. I'm going to move to the next slide. Okay, so the second improvement in the GAN architecture was known as the progressively growing GAN, which was created by NVIDIA, the PGAN. So this is where things started to get really wild, 2018. Okay, so without going too deep into it, what was the difference here with this versus the older Wasserstein GAN? And NVIDIA is like humongous in generative imagery, as you all probably seen in the news and whatnot. They produce some of the most innovative algorithms and innovative technology in this realm that's known to people. So the progressively growing GAN, what it does, and again, I'm going to go only briefly into this differently, is that the Wasserstein GAN was good, but it could produce only low resolution faces. But to get the really high resolution faces, we had to do something different. And so what it did was it started learning on low resolution data and started progressively learning on larger and larger resolutions of data. So the 8x8 picture started with 4x4 pictures, then would start to generate 8x8, then 16x16, and so on and so forth until it got to very high resolution. And eventually it started producing like things that you see to the right. And so this opened an entire massive door to real imagery now could be produced from this, not just low resolution, good looking, good structured faces, but like high resolution faces. So the next improvement was style GAN, and you've probably seen this around, but the style GAN, all this to the left is the style GAN architecture. And again, not deep diving at all into this, but I will say that the few pieces that were added here allowed for I would call it one of the more final advancements into the real deepfake world, in the way that now with style GAN, which what it did was it added the ability, all this on the right, if I try to distill it into English, what it says is it adds the ability to fine control features on a face. So for example, these textures like wrinkles, pores, brow lines, facial hair, all of this now with this architecture on the left could be produced on a face. And this is like almost like the final boss of reality, right? Like now this person looks like they could actually be a real person. If you weren't good at spotting generative AI fake imagery, you would think that this is possibly a real picture. So that's what style GAN allowed. And finally, we got to StyleGAN 2 and 3, and 2 and 3 was introduced in 2021. And so I'm just going to run a video of the article again to show you the parametric control. So see that you can actually play around with this if you go to this article, and you can like change expressions of people, you can change their age, you can change their head orientation. These are all fake people too. None of this exists. Like none of these people exist, but you can make them smile. You can change their ethnicity, you can change gender, etc. Like there's these controls are like, you know, all because of that architecture that I showed you before. And this picture on the right is essentially just to remind you or to let you know with StyleGAN, now you get into entire body composition. Like you're not just limited to faces, but you can pick people on all different like you can create a fake. None of this on the right, this image exists at all. This person doesn't exist. The background doesn't exist. These boats don't exist. None of that is all fake, but it's all generated by advancements to StyleGAN and more advanced techniques afterwards. So I'm going to go to the next slide. So basic operations, and yeah, so there's a lot again in this here. So, but we're going to talk about what GANs a little bit are doing under the hood, kind of in plain English. So there's this technology called in-painting. First of all, let me show you the demonstration of it and talk through it. So in-painting is basically where you're taking the convolutional neural network and you're painting out regions of things, right? And this is an in-painting tool called an in-painting brush. I can like fill out like parts of an image, and like I can use AI to predict what should be in that image. So there's this castle wall, and what I'm doing here in this video, I took this video of myself doing this, is I'm coloring out parts with this in-painting brush and just trying to turn the wall into a plain old castle wall with no holes in it or anything like that. So what happens is how in-painting works, again, it uses on generative masks under the hood. It uses information from surrounding areas of the image to fill out the image of what it thinks it should look like. And it's doing pretty good, in my opinion. Like it looks like the wall had never had any holes in it to begin with. And generative adversarial networks are really good at this technique here. So again, that's a basic thing that they're doing. The next technique is style transfer. And if you're into the world of AI, you've probably heard of style transfer before. So basically what it was discovered with these in the last few years is that you could separate the style of an image from the content of an image. And this is kind of fascinating because, like, you know, this was not known. Like, you know, style, image, they were all thought to be kind of, you know, only a human conception of something. But with the ability of the convolutional neural network to separate features intelligently, it could pick out like, okay, it could take out a style of a painting, like the style of Cezanne, the style of Van Gogh, and whatever, and separate that from what's in the image. And you can combine images and styles and get this, for example, Neil deGrasse Tyson plus this Picasso possibly image to this combination, Neil deGrasse Tyson Picasso image here. And you can do things like transfer between seasons of a scene. So I can use AI to convert this summer scene to a winter scene. And I can use, and vice versa, a winter scene to a summer scene, because I captured the style of winter and I apply it to the scene. And so this is using under the hood. I'm just mentioning what the technique is. It's using what's called gram matrix composition, something to look into if you're really interested in how this works mathematically. But it's computing a matrix, a style matrix, and applying that style matrix to a content matrix. That's all I'm going to mention about that. But this technique has evolved over time into what's called fast neural style transfer. So it used to take a long time to transfer the style of something in the style of, in the style of, in the style of. Now you can do that super fast, and it's only getting faster and faster. So this is something I did, right? A video style transfer. My first style doesn't exist, but basically I took a video of myself and then I applied different styles. So I'll go over one. I applied this anime facial style to me doing this. Again, this was only done really quickly for the purposes of a demo, but real people who spend a lot of time doing this stuff can make some fascinating things. And this is a video of like me on fire, like applying a flaming style to my face or whatever. So again, this is all done in code programmatically in Python. If you're interested, I can go over what that is in the future, what I did. But oops, sorry. Next, let me go on to the next thing. Okay, so the third technique I want to talk about is emotion transfer and why faces are easy to manipulate. The one thing is GANs are really good at manipulating facial structure. Why? Because faces can be segmented into several points. This is called the 68-point landmark model of facial structure, which means that every face, regardless of whose face it is, has these core points in common, or this model of the face. And this is just data. So if you just manipulate these points, you can change the structure of the face pretty easily. And people do this to like create face-like objects, or to like transfer one emotion to another emotion. And I think this is like, I don't know who this is, maybe it's Macron or something, but he has different expressions applied to him through AI by manipulating the control points of his face through this landmark model. Okay, and if you've seen face swap, that's something that people use. So one thing that I did also programmatically using something I call a tool called Deformer and what's called age-labeled cycle GAN, was to generate an image of a person's face. I started with a child, and then I age progressed them through several years. So starting from 20 to 35 to 45 to 55, and at age 70, I changed them from a man to a woman face. So this is basically a demo of how this works. Going over a few of the parameters here. And I run this, it's in Google Colab, by the way. So this is the face that was generated, and this is the progression over the years until it gets to what it thinks. And then it also simultaneously transforms to kind of the male facial structure. So yeah, again, things that you can do with the face, the 68-point landmark model. So the other thing is that the body has something called the pose estimation, and pose estimation allows you to, if you have control points on your face, you have now control points on a body. And you can now segment the joints of a person's body into data itself. And this is like, you've seen these pose skeletons before probably, but a camera can do this and figure out where a person's joints are from just a person's image. And that's called the 18-point model. There are other different models too, but the 18-point is a pretty popular model to do this. So basically, using AI, you can, if you get a person's pose, right, then you can put the person's body into that pose. And that's an advancement over the face stuff, because that's entire body mechanics. And architecture called Pix2Pix HD does this. Okay, so you can actually look at the GitHub online on how this works, and you can actually do this thing of like changing a person's pose from a static image into another pose, and then their body forms around their pose. So you can create fake poses of people. And so again, you can combine this with facial key point systems. That's essentially what we're doing with the StyleGAN architecture as a baseline. We're combining it with face and body, and we can create a whole different pose. And this is just several poses of people here. And this is their pose skeletons using Pix2Pix HD. These fake poses of people that never existed now exist. Okay, so that's kind of like, and if you think about it a bit, this is kind of crazy, because you don't need to have a person pose in a particular way. As AI imagery gets better, you can take one picture of them and you can have them pose in several different ways. So let's talk about GAN tools and deepfakes a little bit. So besides GAN, GAN face stuff, right? Like visual stuff, we also have voice stuff. GANs are good at like working with any kind of data and creating synthetic data outputs. So there's a framework called Wave to Lip that does something called, by itself, there's called Wave to Lip, which then takes a wave file, right? Some voice file, and converts it to the person's lip output. And so it can change the lips based on the sound that comes out of the some recorded voice. So that's in itself pretty scary if you think about it on its own. But this framework uses a generative adversarial network under the hood to do this, because it's using the same game playing process that we talked about earlier to do this. So there's a lot of legitimate uses from this. So you could take like a robotic voice and turn it into like real speech. So that's why you have these AI assistants sounding more realistic over time through voice synthesis, right? And this entire process is called NVC, neural voice cloning. I'll go into that very slightly in the next slide. But you can also do things in turn, and this is basically a process called vocal style transfer, right? I can change one person's voice into another person's voice. As you remember, I changed the style of one image into another. Now I can change the style of one voice into another using wave to lip. This is also programmatic, but you don't need code to do this. There's tools to do this. And new voice samples can be generated. So for example, again, a legitimate, I think, use case of this is that, let's say somebody doesn't speak a native language. You can actually create a native speaking voice from text using this wave to lip framework so that someone can actually understand in a different language something that you're trying to convey. So there are very useful and legitimate use cases for the wave to lip stuff in neural voice cloning. A little bit on the architecture of how this works, the actual voice fingerprinting works. You have a tool or a technique called neural voice vocoding, which is the neural voice coding. And that kind of picks out the shape of a person's voice. This is an old technique actually, but it's used to kind of find kind of like how a person sounds, like their kind of mathematical computational voice fingerprint, and then takes these, what they call cepstral coefficients, and applies them to another voice. So that's how you can change one voice into another. The technology is actually despite all these pieces, if you look into it, it's actually not too complicated. It's involved in signals and system stuff, but those two technologies work together. So now here, I combine both of these things into a little, I call it fun thing that I did.
Trump is doing the most amazing things with generative AI. He's not only the greatest president, but he's also the greatest data scientist. He's making AI great again, okay? Ask Shafik Quoraishee.
So that's me doing this neural voice cloning with 6 gigs of Trump monologue training data. And I created this, essentially a fake of him to say this and say that I, or did this presentation or whatever. So again, this is using those things, wave to lip frameworks, those neural voice cloning techniques and everything like that behind the hood. And this is essentially, if you want to do the hard way of doing deep faking stuff or whatever, or whoever's doing it, there's a lot of work that went into this. This took hours and hours to do. But
Trump is
okay. But just so you know, now there's something which I call the Photoshop of deep faking, which is there's tools called Deepfakes Lab and Deepfakes Live. And these tools have been out for a while, but what they do is they allow you to create deep fakes, essentially, of people, and very high quality ones. The Deepfakes Lab lets you take faces of people and turn them, like, using their structures, like, manually into other people's faces. And it's a very lightweight model, actually. Like, so you can, it used to require that you run this software on like a high quality, like NVIDIA GPU, and like you still need some high quality machining to do this, but you could actually run this on Colab now, apparently. I haven't done that, but you can run this on the cloud and do offload that work to the cloud. And so with this, the tools are, if you look it up, you can actually see the tools are actually quite involved, and they do a lot of different things. But and it has a very active community, but the really powerful mechanic behind here is the Deepfakes Live stuff, which lets you do this live. And I'll show you a demo of that as applied to.
But life cannot just be about solving one miserable problem after another. That can't be the only thing. There need to be things that inspire you, that make you glad to wake up in the morning and be part of humanity. That's why we did this. This guy called Tsiolkovsky, one of the early Russian rocket scientists, the great saying, Earth is the cradle of humanity.
So basically, that's just to show you that this can be done live. This was from a site called Deepfakery, which uses Deepfake Live, Deepfake Live and Deepfake Lab to do this kind of stuff. And this can be done very fast on very high powerful machines. And so you can do this with any live video. And the examples are actually kind of fascinating on there. So I'm not going to go too deep into that because we're going to just move on because there's still a few things to cover. But the next thing I want to talk about is what's the idea of the first order motion model. So the first order motion model, this is where stuff now gets really off the hinges, because before everything was using data and faces that we already had. Right now, this is something much more complicated, actually. Motion models are used for motion style transfer itself. So say you want something to move in a particular way. We talked about visual styles. We talked about vocal styles. Now you have motion styles. So you can actually convert one type of motion to something completely different. And this is so the example I'm going to show you is from MyHeritage. And you take a image and any image. I took an image of a 15th century family. I literally looked on Google, took a 15th century family image and applied this here. And what you do is that it essentially uses those key points we talked about to guide the motion transfer in novel ways, not even explicitly attached to a video. So I can make something that who knows where the data came from, the motion came from. I can turn it into something completely different. So, and again, this is like a self-supervised kind of approach. We won't go too deep into what that is, but I'll just rather show you the demo. And yeah, this is Animate Diff is like the newer stuff that came out. I saw a note about that. This is 2021. You can actually do like stuff with like epic realism, animate diff through stable diffusion, to actually do like some much more fascinating things in the modern day. But this is kind of like doing this, and to me, this is kind of like, you know, when I first saw this a long time ago, this was pretty interesting and creepy. But you can, you know, all the faces in this image are animated, and you could try this and take any image and do this. Okay, so we'll go on to the next thing. I think yeah, so we have a little bit more here, but I will kind of just demonstrate how I use this technique to do this animation on my own using thin plate spline motion models, TPSM. So this is like kind of the thing that came out in 2022 and 2023, where you use a fake, you can take any fake image, and then I'm taking a video of myself doing this and going to this site called Civit AI and applying this thin plate spline motion model here. And what you'll see is this is a generated AI image. Again, someone created it from their thoughts or whatnot. And then we applied this model and I run it. Again, this is kind of the Python setup for this. And we'll just get to the crux of it because I am running out of time a bit. But so this is me with this face here. And if I run this, if I go to what it looks like, and as you can see with my face, I've made this thing kind of move on its own. And you can do this with any kind of thing. So anyone who's like really involved in this world, like this is stuff that they probably use now with like stable diffusion and things like that. But on its own, this is again kind of like what's making a lot of the deepfake stuff more popular these days. And I'm going to play this video, which kind of drives that point home from a site that I found.
You gotta hear the truth. What you are and what I am. You never told the truth for 10 minutes in this house. Well, hear this, Willie. This is me.
Again, totally fake thing that was generated and applied to movie animations. And so I'm going to quickly go over the stuff related to deepfakes. The deepfakes timeline. Okay, this is actually, to me, important and an important indicator of where things are headed and where things are headed over time. And so it started off pretty much with GANs, right, in 2014. That's the real timeline. And I highlighted the main points. In 2017, the video of President Obama came out lip syncing, essentially creating a whole new like video out of President Obama, like that he's something that he never said before, but using his voice and his face. neural voice cloning proper came out in 2018, and that allowed attaching of voices to images. And then wave to lip came out later on, and wave to lip allowed that brought the whole thing full circle. And with that, with all the other generative AI technologies, advanced GANs, stable diffusion models, animate diff, which was mentioned earlier, tons of other things. Now you get to these core things on this timeline get us to where we are today. And where are we today? Well, this summer, we had
Alan Wink News, a viral deepfake video has surfaced depicting Governor DeSantis announcing his withdrawal from the 2024 presidential race. Now, this video has sparked numerous questions. The user who initially shared the video on X, formerly known as Twitter, did clarify that it was a fake creation, but it didn't take long for other accounts to get a hold of that video, presenting it digital landscape. What's being breaking news?
The videos are downright dangerous. They're being used in some ways as jokes, but have potentially devastating consequences.
Deepfakes are
so basically that's a video of affecting the current election, right? And then this is a video of surrendering in Ukraine. And most people see these as fake. These are quite easy to see, like if you're paying attention, but not everybody. A lot of people thought these were real videos. And so the number of people that will be thinking that these videos may increase over time. And that's kind of the whole crux of the problem here with this technology. So
Alan Wink News, a viral deepfake video has
and then so just quickly going over some numbers. The doubling of deepfakes in North America from 2022 to 2023 in the first quarter, there was a doubling of them. The impact on companies. So smaller companies in the last year or so lost about, and larger companies lost a total about $480,000. Not actually that much, but over time it actually adds up, right? And the number of deepfakes has gone exponentially over the last from 2018. Every year, more and more videos deepfake videos are coming out that are very realistic and fooling more and more people. And again, a 900% annual rate of increase over the last year of deepfakes that have come out, despite this technology being out for quite a while in generative adversarial networks. And again, it's predicted by 2028 to cost about $348 million worth of the market itself is going to be humongous at that point relative to what it is now. And so this graphic on the right, if you take a look, is essentially just kind of how the rate of all these different types of deepfake identity fraud kind of things are escalating. So you have synthetic identity fraud, which is the creation of false identities. That's escalating year over year. The voice deepfake issues, fake voices over the phone from fake robocallers are increasing. Video deepfakes, the threat is increasing. Overall, that these are escalating upwards. And there's attempts to try to solve this problem, but this is one example. And Intel released this thing called Fake Catcher in 2022 to combat the deepfake rise. And one of the things that was novel about it at the time was that it looks at deepfakes to look for like weird things, like artifacts, like flickers and like facial structures that don't make sense. And the other thing that it looks at that really gave it a boost at the time was biomarkers. So it looked for things like when people talk and they're flustered, their blood, their facial hue changes. Many deepfakes did not take that into account initially, and many deepfakes were spotted that way. But as all technology, deepfake technology has increased in its ability to even defeat the fake catcher tool. But you can follow what's going on with this tool. So I have 2 more slides and then I'll be done. So where are we today? So I'm just going to play a quick video from the left for those who are not familiar with this, but this was in December, this was a popular story.
Hello, everyone. Today, we're going to talk about a fascinating development in the influencer marketing world. Meet Aitana, Spain's first AI model, who is not just turning heads, but also generating a significant income of up to $10,000 a month. Aitana is a 25-year-old pink-haired woman from Barcelona. But here's the catch. She's not real. She's an AI model created by a Spanish design agency named The Clueless. She has quickly amassed over 121,000 followers on Instagram and has become a lucrative influencer. The Clueless agency decided to create Aitana to overcome the challenges associated with human influencers. Aitana is reliable, doesn't have egos, and doesn't demand high fees like real models. She can be controlled in a much more granular manner, making her an excellent asset for brands.
So that's where we are, like corporate embracing of this as well. Like this is not only used to fool people in like fake political videos. This is the nice little thing for those who haven't seen it, with using stable diffusion and control net. And also GANs, because GANs are involved in this process too. So this is creation of like, you can see for yourself where we are right now.
Maybe I'm a gangster too, and it takes two to tango. You don't wanna mess with me. Maybe I'm a.
So again, and last video is this last video of
Hello, and welcome to
a
Channel
news
One,
channel. It's
a
the
new
first
way of
Channel One news.
consuming, reporting, and thinking about the news powered by artificial
So
intelligence.
none of these casters are
Today,
real.
you'll witness AI-generated stories and headlines, captivating visuals, and data-driven insights. From global news to finance to entertainment, we'll show you how technology enables us to bring you a global perspective 24/7, right from the heart of our AI-native newsroom.
So anyway, what this channel does, it generates false newscasters, and it presents the news in different voices with different generated actors, and essentially, okay, so this is the end of my presentation, but the last thing I'll note is that all of this has kind of led to this world right now, which is becoming challenging to navigate as you see these issues arise. And it's a constant cat and mouse game, really. The interesting thing from a technology perspective is that 10 years ago, this technology, started off with like little faces and like little low resolution images. And now we're here kind of in this world. And I think the best way to kind of navigate this is to kind of learn, this technology as best as you can and kind of be aware of what's going on so you can understand how to, I don't know, kind of like ethically figure out how to deal with this in society, because as society does have with this technology a huge ethical issue overall, as you can see some of these examples that have been presented. And yeah, so that's pretty much the end of my presentation. I put some notes in here, some resources, and there's some more that you can find. These are constantly being updated. And yeah, but so thank you for my talk, or to attending my talk. I'm going to stop sharing now. And